Okay, and I'll turn it over to Dean, who will formally introduce our speaker for today.
Thanks, Ed. It's my pleasure to welcome Professor Cady, who earned his BA and PhD from Cornell University in Ithaca, New York, and is currently an Empire Innovation Professor of Nanobioscience in the College of Nanoscale Science and Engineering at SUNY Polytechnic Institute. Professor Cady has active research interests in the development of novel biosensor technologies and biology-inspired nanoelectronics, including novel hardware for neuromorphic computing. He is also the executive director of the SUNY Applied Materials Research Institute that funds collaborative research efforts between SUNY faculty and industry partner Applied Materials. So welcome, and we'll be happy to hear from you.
Thanks, Dean and Ed, and thanks to the alumni for inviting me, or the Emeritus alumni for inviting me to give this presentation. I will share my screen now. Great. So hopefully everybody can see me. Thumbs up, Ed and Dean.
Yeah.
Good. Okay, so again, my name's Nate Cady. I'm at SUNY Polytechnic, just across the street from the main U-Albany campus. As many of you probably know, and I'll go into this a little more detail later, we were originally part of University of Albany, first as a program, and then a college, as a College of Nanoscale Science and Engineering, and around 2013 or 14, I have it in a timeline coming up. We ended up splitting off and merging with SUNY IT out in Utica. And as probably you saw in the governor's State of the State, there's rumblings that maybe at some point we will come back into the fold with U-Albany, but I'll let that come up later. So at SUNY Polytechnic, our focus is on, main focus, at least here in the Albany site, is on nanotechnology. And so I wanted to go through a really quick primer on nanotechnology. Most of you probably know this, but I will just go through it quickly because it's kind of fun. So nano is just a size scale. So for reference, most of us are in the 1 to 2 meter height range. Click here. Red blood cells in our bloodstream are about 10 micrometers, or 10,000 nanometers in size. So a nanometer is 1/1,000,000th of a meter. Bacteria, is shown here as E. coli, are around 1,000 nanometers, or 1 micrometer in size. Of viruses, this happens to be Ebola virus, is 100 nanometers in size. So that's a 100 billionth of a meter in size. DNA across the double-stranded double helix of DNA is about 2 nanometers. And we get to the atomic level, we're talking sub-nanometer. So on the order of a small atom, about 1 angstrom, or a tenth of a nanometer in size. So this should give sort of a size perspective on the types of things that we're dealing with over here at SUNY Poly at the College of Nanoscale Science and Engineering. We tend to manipulate matter mainly on the size scale of the 100 nanometer down to almost the atomic level. We do some bigger stuff as well, but our sweet spot is kind of this 100 nanometer and smaller regime of where we're manipulating things and building structures. So that's nanotechnology, the size scale, and then also the idea of being able to use matter or manipulate matter at that size scale to do different things. A lot of what we do here is related to computer chip or semiconductor manufacturing. So how to build better microchips, better transistors, better components that are part of those chips. But as it was mentioned during the introduction, my background's really in biology. So I'll tell you later about how we leverage some of these things to help with biological studies, whether it's fundamental biology or for doing applied things like biosensors, or even building scaffolds for different types of healthcare related activities. So I want to give a couple of examples of how we manipulate matter, how we pattern things at this very small size scale. So one of the things that we do a lot over here at the college and in the facilities on site is we use light, a very short wavelength light, so typically 193 nanometer wavelength of light. We have some new tools that use light wavelengths down into the 14 nanometer size range. And we shine that light through something called a photolithographic mask or a reticle, and that's shown here. And I hope you guys can see my pointer. I don't know if you can or not, but on the left-hand side of the slide, there's a beam of light going through a little square. And you can think of that sort of like back in the day when we used film and had negatives after taking a picture. This is like shining light through a negative. It then goes through a series of lenses, and then the image gets shrunken down to a smaller size and shown onto one of the substrates that we use, which is a silicon wafer. And so this big structure over here in the middle is a 12-inch diameter or 300-millimeter diameter silicon wafer, where we've imprinted a lot of these patterns using light onto the wafer. And all those little squares are replicates of the same thing across the entire surface of the wafer. And once we do a few steps after that patterning, which includes a developing step, and then we can do things like etch or deposit another material. And shown here is some cross sections after we went through an etching process. You can see that we got this wave-like pattern on the surface. And that's after we've chemically etched down into the surface of that wafer to create that topology. And then the next black and white image down is where we're showing where we've deposited a couple layers of metal on top of this structure. So each of those little fins sticking up is nominally in the 50 nanometer range in width, and the spacing between these fins is on the order of 500 nanometers. So it's give or take depending on how we've done the etch conditions. So this repeating pattern every 500 nanometers of these skinny little fins. And it turns out this makes a little optical structure, and shown in the color image in the center now is one of the chips that I'll show you later that we use for biosensing. So we actually have in this process created an optical pattern on the surface of these chips that we use for our high sensitivity biosensing project that I'll tell you about. So what's over here at the complex, most of you have probably driven by or at least seen it, whether you're going on I-90 or Washington Ave Extension or up Fuller Road, you've seen this complex. It started out as the building called NanoFab 200, or the SESTM building. And so the Atmospheric Research Office was there, the Atmospheric Sciences Department and NOAA were all there, in addition to what eventually became SUNY Polytechnic. And there's still some laboratory space in that building that we use for doing things like chip fabrication. And then the rest of the complex really grew up around that. So some of you may have seen some of the first buildings come up, like NanoFab South and then NanoFab North. Eventually, this large building that I'm in right now called NanoFab East, which I realize doesn't have a label, but it's the bottommost building that kind of points towards Fuller Road, shown on this map. And that's our site. So we have all of these buildings that primarily contain clean room space. And clean rooms are these giant, essentially laboratory type rooms where the air is constantly being filtered to remove particulates and is tightly controlled for environmental conditions. And it's where all the equipment is housed in order to do the fabrication techniques like I showed you in the last slides. So we have thousands of square feet of clean room space and this equipment to do this R&D. Lots of industry partners. You may have heard names like Tokyo Electron, Applied Materials, IBM, Global Foundries. So lots of these companies are doing their R&D on site. And really, what I like to think of this space is it's sort of like a pilot facility. So we're not really a production facility. We're not producing chips that are going into anybody's cell phones or cars or any other devices out there. Really what we're doing is the research and development stage to make parts of those chips or parts of the process better, faster, less expensive. And so we work with many different industry partners to do that here on site. One of the other institutes that's here on site, besides all of the semiconductor players, is an institute called AIM Photonics that uses, instead of electrons to move information and data around on chips, it uses light. And so that's a kind of a cool new initiative over here that's been going on for the past few years. And just for information, that these facilities were really funded in main part through New York State investments, as well as all the investments through our partner industry partners. So for instance, the state puts in dollars in order to build infrastructure, and our industry partners tend to pay to basically rent space and pay to do processing and their R&D while they're on site. So a quick timeline. So back in the late 90s is when that first building it says here NanoFab 200, it's also known as the System building, was built. A lot of the big landmarks on this timeline were when big partners came on site. So Tokyo Electron is one of the major equipment providers for the semiconductor industry. This is where they came on site. ASML is another big partner. Companies like IBM and Global Foundries are manufacturers. IBM is not really in the chip making business anymore, but really more in the chip invention business. And then consortia like Semitech also were on site. These types of consortia pool resources from a lot of our industry partners in order to do research. You'll see over here later in the 2000s is when this original split from UAlbany occurred and our merger with SUNY IT. I think in the 2014 era is the exact merger date when we started to have the fully joint programs with SUNY IT, and the umbrella of SUNY Polytechnic was coined. So that's just kind of a brief timeline of where we are and some of the key partnerships that came about during this time frame. So what's the impact of SUNY Poly? So really with all these industry partnerships and the work being done here, really in the industry space and the R&D space, the overall investment has been somewhere in the order of $24 billion, which is a huge number. There's over 3,000 jobs on site, and across upstate New York, I don't want to get into it today, but there's many other satellite facilities across the state. There's somewhere on the order of 15,000 jobs that are supported by this entity. The facilities infrastructure is huge, and I didn't check to see if this number agrees with the former slide. The numbers actually just keep growing as more and more goes up here, but thousands of square feet of facilities and infrastructure space. And down here, this number usually is always increasing. This is the number of industry partners shown at 300 from across many sectors. So obviously the electronics industry, but also partners from the energy space, defense, biohealth, a number of different industries are leveraging these facilities here to do R&D. Okay, so that's a lot about what we do and what we are from an infrastructure and an industry partnerships point of view. What do we do from an academic point of view? So we offer a few different programs here locally on the Albany campus. We have other programs under this umbrella of SUNY Poly at the Utica campus, but today I think mainly we'll talk about what's going on in Albany. So we have PhD and master's degree in degree programs called nanoscale engineering, nanoscale science, and nanobioscience. We have a Master's of Science in Advanced Technology. That's a partner program with the Utica campus. We have bachelor's degrees in nanoscale science and nanoscale engineering, and we've gone through ABET accreditation for the nanoscale engineering program. Otherwise, we're Middle States accreditation for the rest. So to go through the Middle States review, as some of you are probably familiar. Departments within the college here in Albany. So we have a nano engineering department, a nanoscience department, and a nanobioscience department. For a while, we had a nanoeconomics program, but it was never a formal degree program. But we do have key faculty who have some emphasis in economics as well. So I'll go quickly through each of these departments. We initially coined these as constellations, but it's probably most translatable to call them departments. So in the nanobioscience department, we have a number of faculty who come from different backgrounds. So for example, Susan Sharfstein and Yubing Shi are both from a chemical engineering background, while the rest of the department is mainly from a biology background, with the exception of Professor Brainerd, who has a chemistry background. So we're fairly interdisciplinary as it begins. And my department chair put this slide deck together. So we do research related to things like biosensors. There's a number of faculty who participate in the RNA Institute and do RNA related research. And we collaborate closely with folks at UAlbany. Basic protein biology and protein structural research, and then a lot of cell biology as well. Translating mainly into the cancer and stem cell spaces would kind of characterize most of the work going on over here when it comes to actual cell bio. For the nano engineering department, really folks in this department come again from a range of different backgrounds, some with more of a material science and materials engineering background, some of the more physics background, and some of the straight electrical engineering background. And so research here really ranges from new types of electron devices. So these can be things like transistors. They can be new types of photocells for doing things like solar, and a variety of work, even going into the energy space of new materials that could be used in batteries, solar cells, and other things. So really a range of different research in nanoengineering. And then nanoscience is the biggest department that we have over here, and really a very wide range of background for these professors. Physics, material science, and a number of other degree backgrounds for all these faculty. And there's some really cool work going on in fundamental research into materials themselves. So here's an example in the bottom right of looking at ferromagnetic materials and some very high resolution microscopy and analysis of those materials. Fundamental work in some of the techniques used, such as E-beam microscopy. Sorry, this is E-beam patterning, but using electron microscopy to do analysis. And then again, fundamental properties of materials. This is Vince Labella's work measuring the Schottky barrier height for materials, which is kind of a measure of being able to conduct across a particular barrier. Okay, so that's a flavor, at least, of the types of faculty and research programs going on over here. Just a quick list of things going on. Advertisement is for the years 2020, 21, there was $35 million in research awards, with around 11 million in expenditures within that time frame. Because a lot of those awards are multi-year awards. 170 publications, 90 or more national, international presentations, 11 patents or patent disclosures. We do a lot of capstone projects with our undergraduate students, and what's interesting is some of these have started to be supported by industry partners. So rather than just students working in faculty labs for their capstone research, we're getting more and more industry partners to support that research, or at least provide topics for that research. And then we tend to do quite a bit of outreach as well, a lot of community-based outreach to teach about nanotechnology or talk about the college and the programs going on here as well. Okay, and then what do our students do when they leave? Well, as you can imagine, on the site here, we have all of these industry partners doing their R&D. It becomes a really great environment for students to do internships or work with these companies while they're a student. This slide really speaks to what our undergraduate students are doing and doesn't actually reflect the graduate students, but 60% of our undergraduates end up going to industry, while 40% go to graduate school. And out of those students going to industry, many of those are going to industry partners that are on site. So for instance, multiple of my students have gone to work for Tokyo Electron, and now several for Applied Materials, both large semiconductor companies that are on site. Many students going to companies like Intel and IBM as well. And so really what happens is there's sort of a niche in the training that students are getting, not only in the examples they get during coursework, but also through their experiences with doing internships or even just interacting with some of these companies, being right here on site, is that they definitely have an advantage in that they're familiar with the terminology, they're familiar with the environment, which is a little less of an academic environment over here, a little more of a professional environment. And these companies really tend to love our students and snatch them up very quickly with offers this time of year, actually. So they're really trying to grab the best students out of our program and hire them right out of their undergraduate degree into school. Interestingly, too, is that many of these undergraduates, when they start working for companies, especially when they're on site here in Albany, many of them tend to enroll in our graduate programs. And so in parallel with them starting their new job at the company, they're also enrolled either part-time or sometimes full-time in either our master's or PhD programs. So that's another actual benefit for us, because we're getting tuition and enrollment. At the same time, the companies tend to offset some of those tuition costs. And so I've had several students who completed their degree work for their graduate degree on their company dime, and they were able to stay right on site doing that. Okay, a couple other little things about what we do over here. So I mentioned AIM Photonics in one of my earlier slides. This is a wordy slide that I got from someone else, and I won't spend much time on it, but many of you are familiar with the idea that microchips are using electrons or electricity to move data and make computations. And one of the newer technologies is to take what's been done in things like fiber optics and move all of those light-based operations onto chips. So we use this same wafer-based platform, these large silicon wafers, just like we would make electronic-based chips. And instead of using electrons, we use light to move data and do computation on those chips. We call this integrated photonics or silicon integrated photonics. And it's really all the rage in industry and is being used for very fast data transfer, very fast computation on chips. And we are one of these American Institute for Manufacturing, AIM, that's that acronym, sites, which is meant to advance manufacturing in particular areas. And so we're doing this in the photonics space. And you can see here, it relates to data and telecom, sensors. I actually work on a project that's a AIM Photonics biosensing project, radio frequency type of applications. If you've heard of LiDAR, can be done off chip, but it's now starting to be performed with this type of integrated photonics approach on chip, making it cheaper and faster and easier to do things like LiDAR, which many of your cars probably have that for detecting collisions or collision avoidance. Okay, one of the other things we do is a lot of what I would call economic development related activities. This is leveraging the fabrication facilities and the environment here to do work to help small businesses within New York State to do technology development. So we have two centers for this. We have a Center for Advanced Technology and a Center of Excellence, both in the nanotechnology regime. And the type of thing that we do in these initiatives and under these centers is to help basically fill in these arrows. So if a company or a group is doing research and they need to get to the development stage to try to maybe turn that research finding into something that could be a product or the beginning of a product, we help bridge that gap. And we also try to help in the next phase, which is once the company or the entity has figured out how to build their technology and how to make a small volume of that technology, how do they actually get it to higher volume production and eventual deployment? And so we try to basically be the bridge where these arrows are shown in order to bring technologies to fruition. And so there are several companies that have incubated on site here, some student-initiated companies, and then a whole slew of research projects where an outside company within New York State is working with a professor or a researcher here to do one of these stages of kind of moving the arrow forward. And one more thing, and then I'll tell you about my research in just a few slides. The thing I want to mention is some other public-private partnership activity. This is one example, and I can talk about it in more detail because it's related to this company that's shown in the upper right, Applied Materials. Applied Materials is, I think, the biggest equipment supplier in the entire semiconductor industry. So they supply the equipment and tools used to make chips. Probably a lot of you have heard about the chip shortage or the semiconductor shortage going on right now that's delaying all kinds of products. Applied stands to make a lot of money off of this as more and more of the semiconductor manufacturing companies ramp up and build new facilities. But their partnership here on site is really to do R&D on their new equipment. So they basically filled out an entire fab space here on our campus. And by fab space, I mean a part of a clean room where they installed much of their new, latest and greatest equipment. And they do R&D to support their potential customers. And we basically get access to their tools as well for doing our research. And the other partners on site also have access to that equipment. So in parallel to Applied Materials making that investment here in New York, they also partnered with SUNY as a system under this partnership called the SUNY Applied Materials Research Institute. I'm the executive director for this program, and what it really is a matching funds program. So the idea is to take areas where Applied Materials is interested in doing research, finding the correct partner within the SUNY system, so the correct researcher or professor who has capability to be able to do research in that field for that particular topic. And then for every dollar that Applied Materials puts in, SUNY matches with another dollar to support that research activity. So we funded 5 projects in our first year, which were started in fall 2020. We have another 3 starting up. And we've essentially funded projects at all 5 of the major SUNY campuses, including UAlbany, Buffalo, Binghamton, Stony Brook, and SUNY Polytechnic. So all the big research campuses have projects going on right now, and we hope to just keep increasing the number of projects as we continue with this partnership. And that's me, and then this is the rest of the leadership board for the Samurai. Okay, so I know I have probably 5 or 10 minutes left before we'd like to have some time for questions. So I figured I would tell you a little bit about my research group. So this is me. This is a picture that's about 1.5 years, 2 years old. I guess it's pre-COVID because we were out having a lunch over at Cityline. But this is most of the people here in this picture are still part of my research group. Post-COVID, I think we need to have another get together so we can refresh our picture. But we do a variety of things in my group. So as I mentioned, I'm a biologist by training. So my degree is in microbiology. But during my graduate and postdoctoral work, I really was basically finding the niche between microbiology and biology in general and nanotechnology. So when I was at Cornell, I used their nanofabrication facility to build what I would call little widgets. So these would be little chips that we could use for things like biosensing, to detect some biological target, or to manipulate how cells or proteins might organize themselves or interact or operate on a surface. So my group continues to do that. And in the topmost stripe up here, I'm showing, topics of how do we use nanotechnology to understand fundamental biology. So we build platforms like microfluidic platforms. This is little teeny fluidic circuits to be able to manipulate very small samples and make measurements or do imaging. We manipulate both cells and proteins at a very small scale. Here we printed the CNSC logo with very tiny bacterial colonies. We do a lot of work on biosensors, so physical structures or systems that we can use to measure some biological event. In the middle stripe, I'm showing how we use nanotechnology to do more applied biology. So this is the case where maybe we want to make a scaffold material or a substrate to grow cells on. This could be for something like a stem cell project where you want to give a structure for cells to grow on and then see how they derive into other types of cells. So ask a fundamental question, or we're making a substrate to grow a specific tissue. So how do you grow some tissue to go into the eye that's structured in the right way with the right cells? We've done other work where we've patterned surfaces to make them more or less favorable to cells attaching, both for bacteria and also for mammalian cells. And so a lot of that work really was focused on anti-fouling. So how do you prevent things from sticking to the surface? But we can also leverage that in the other direction to encourage cells to attach. And then the bottom stripe is where we sort of think of biology as an inspiration. So how do we take a phenomenon in biology, like shown on the far left, the creation of a neural synapse or the maintenance of a neural synapse, and how do we mimic that with an electronic structure? So a lot of my work now that utilizes our nanoscale fabrication facilities is focused on building these electronic devices that very much mimic the way a synapse in the brain functions. And we're trying to leverage that for doing things like neuromorphic computing or artificial intelligence research, where you need to mimic those biological learning properties and structures. So sort of quickly here, I'll give you a few snippets or examples of some of those specific research projects. So in the biosensors field, one example, we're doing work on detecting Lyme disease and also more recently antibody response to COVID-19 infection or vaccination. And so one of the things that we do is we can take proteins from bacteria or viruses. We can express them and then print them onto chips. And this little gold chip in the bottom is, I foreshadowed a bit, it's the same chip as one of the ones you saw in the first few slides. This had that nanostructured pattern on it. And if you can see in your computer screen, each little dot on this chip is an individual, it's not an individual protein, but it's an individual spot composed of just one type of protein. And we use those to help identify, oh, this is a repeat slide. This is that structure I was telling you about that you saw before. And on that structure, when we print these proteins that I was telling you about, we can label them and with a fluorescent dye, and we can see them very brightly as bright spots if we have the right interactions going on for this sensor to be operating. And we need that grading-like structure, this repeating structure, in order to get that what we call fluorescence enhancement, in order to get these bright spots. And I'm not going to bore you with too many details, but this is an example from COVID-19. We take proteins from the virus. So you've heard of spike protein. Some of you may have heard of nucleocapsid or the N protein. These are all targets of the over-the-counter antigen tests that you're probably all buying and using right now. And we literally put those proteins on the surface of the chips. And we look for these black antibodies, which are antibodies from a person's blood after we collect blood. And then we label those with a second labeling antibody. And if we get this interaction to occur, the one shown on the left side where the green target was, we get these bright spots. And this means that we had a successful binding of a person's antibody to a particular target. And I'll show you the type of data we collect. So this is the type of data we collected from people who were vaccinated with different vaccines, who had been hospitalized with COVID or just sick with COVID, never infected, or those who were both vaccinated and had actually contracted COVID at one point. And what we're measuring is the different levels of antibodies in all of those different people, depending on their exposure. And so we can quantify it, and we can say that with fairly good certainty that folks who were both infected and vaccinated, which should be somewhat obvious, have the highest level of antibodies as compared to all of these other people. So we're able to make very quantitative measurements of antibody levels in people against specific targets. We're doing this for variants as well. And so I can add to this list now, we do have Omicron as another variant. And so what we're trying to do is be able to make a chip that lets us show a differential or measure a differential between how people's antibodies bind to, for instance, the original COVID-19 versus all these variants coming out, which may be somewhat predictive in telling us how people will do against the different variants if they should become infected. We do work on microfluidics, as I mentioned, as well. And this is a one-slide example of how we're working with some collaborators to make what we call imaging windows. This is a little glass, teeny little glass window that gets surgically implanted into mice or rats. My student is really working on fluidizing this window. So we're able to basically build a microfluidic structure to deliver drugs or imaging agents into the mouse. And the reason for the window is that you can actually do microscopy into the mouse and observe cell-based interactions going on inside that mouse. So our collaborators down at Albert Einstein College of Medicine use this for imaging tissue, cancer cells when they leave from a primary tumor and actually make it into the bloodstream. And they're studying literally intercellular activity as cells do that. And so we're providing this means or this technology to allow them to do the imaging while at the same time delivering drugs or other reagents to be able to, for instance, stain and differentiate one cell type from another while they're making those measurements. Okay, last thing I'll tell you about is the electronics stuff that we're doing. So really we have this pipeline, and I think I illustrated this before in some of my other slides, where we can really take a lab-based discovery and try to get as close as we can to making a product at the end of the day. And so my group studies a few devices in this first category on the left, called either memristors or ferroelectric switches. So we're making devices in that category that act sort of like a synapse in the brain. We can work on it from the fabrication standpoint the packaging standpoint, which is really where we are right now, and then eventually handing this off to a manufacturing partner to be able to make a whole lot of devices that could then go into a product someday. And so I mentioned before, we use these clean room facilities to do the fabrication. We use techniques like photolithography to make very, very small structures. And then we use a variety of other techniques after that to basically layer many different material layers with different 2D topography, or sorry, 2D layout in many different layers to build an overall electrical computing chip. And the structures that we're making are these little memristors that are built in conjunction with another device called a transistor. And when you put all that together, these devices act like a neural synapse, in the idea that a neural synapse, when you're forming a memory, basically makes a better connection between two nerve cells. Our devices, as we use them, make a better and better electrical connection. And that connection is what we call non-volatile. So it does not, we don't lose it when we turn the power off, it stays. And so we've made this semi-permanent connection now between two different neurons, if you will, and can use that to store memory information, but also in a neuromorphic computing or AI context, we're literally storing memories and updating memories as you're teaching the system to learn. So we're really truly replicating something that you would normally see in the brain. So that's the end of my slide. I think that's probably a good point to stop anyway, so I can take questions, and I would be very happy to answer questions that come up in a chat or verbal questions. And once again, I really thank you for the time to be able to tell you about not only what we do over here in general at SUNY Poly, but also what I do at my research group.
Okay. All right.
Wow, that was so much more than I could have ever imagined, to be honest with you. Thank you so much for such a wonderful look at what goes on there.
No problem.
Yeah, no, I definitely agree. It's just across the street from you, Albany, but it's a whole different world. So most of us aren't really aware of all the activity going on over there. I guess you can close the slides now if you want, Nate.
Sure. Yeah, if anybody wants to ask a specific question, I'm happy to pull them back up.
Okay, so why don't we start the questioning? Again, if you have a question, use the raise your hand feature. I can probably get the ball rolling here. I was wondering, Nate, if you could talk a little bit about your undergraduate program, like the curriculum. For example, obviously, many of their courses are going to be engineering or science based, but what about a more general education curriculum, like in the liberal arts or humanities? And if you do require courses in that area, do they take them at UAlbany? Because I can't imagine you have like English or history professors in your school. So where would they get these gen ed courses? And I guess also, like, approximately, you might have mentioned this and I maybe missed it, but how many undergrads do you typically graduate every year?
Sure. So I'll work backwards a little bit. So as far as overall numbers, while we were still part of UAlbany, we'd actually ramped up to, we were on track to having nearly 100 students per class. And so for a variety of different reasons, after we merged with SUNY IT, we kind of plateaued and we've gotten down to smaller class sizes now. So our current class size is in the 20 to 30 students. So we're kind of the size of a department, really, if you think about it from number of students per class in our undergraduate degree programs. The intention over here was always to ramp up a program with probably 400 or 500 students in the program. So graduating, somewhere in the 100 or 120 students per year was the original, how we envisioned the program. And I think we'd like to return to that track as soon as we can, because we can sustain it. For general education, we still follow all of the SUNY-wide requirements for gen eds. So we do have to follow the SUNY gen ed policies. You're right, we don't have our own English or foreign language or many of the other courses within the college here. So currently what our students do is they either take those courses through SUNY Poly in Utica. So there's a lot of distance learning that they can do. I believe it was last year we signed the formal MOU with UAlbany to be able to cross-register. So students now can cross-register both ways, from UAlbany to here and from here to UAlbany, I believe with no impact at all on their tuition. So that gets dealt with at an institutional level. So we're back to having the option of students being able to take coursework at UAlbany, and likewise for UAlbany students to be able to take coursework over here. So that's an option again. And you're correct. A lot of the coursework that's for the degree itself is either science, math, or engineering in nature, and that's all taught here within our walls. So we're able to field all of those courses.
Great, good. I think Glenn Griffin has a question. Let's see if we can unmute Glenn. Let's see if I can do that. Allow it to talk. Glenn, if you can, yeah, there you go. You should be able to ask your question.
Yes, can you hear me now?
Yep.
Yes.
Yeah. So Nate, thank you for a wonderful and interesting presentation. I was just wondering, among the last things you said, in terms of improving connectivity between what you're sort of reluctantly calling synapses, to store memory. Can you we extract memory therefore?
Yeah, so electronically, we do this in a couple of different ways. We make what we call a straight memory array. So we build kind of a high density array of memory where we can input values and we can do something we call nudging. So we could set a memory value and then we could nudge it up or nudge it down. And this is more like what a brain does with a synapse. It doesn't necessarily have to be all on or all off. It can be sort of on, sort of very on, all the way through a continuity of different states. So we can store memory that way. We can also make a circuit where instead of writing memory to a big data table like that, we can locally store memory where we're doing a computation. So one of the problems right now with computing is that our processors and our memory are very fast and they're able to make lots of computations, but there's a lot of moving information around. So information goes from being processed to memory and then back and forth. And so one of the things that people would like to do more of is to do computation in the memory or have memory very close to where you do the computation. So we can do that as well. We can store that information very close to the circuits where we're doing the computation. And we basically can store and look up. So we can always write data and then we can read data back out. I think that's what you're asking, but yes, we're able to both store and extract that memory information from a circuit. We haven't figured out how to do that between biology and the chips yet, but that would be pretty cool.
Well, just quickly and then shut up. And that's exactly what I'm sort of projecting towards and finding exciting. I mean, if you could extract from, the biological creatures like ourselves, I mean, wouldn't it be amazing in terms of whether it's Alzheimer's or whatever down the road, what you could do in terms of capturing that memory? It'd be fantastic.
Yeah, I think that's so what we're doing that sort of fits with that is that, so I had a student working on it was a correlation problem. So if you have lots of data coming in and you want to correlate signals with some activity, she was doing that and storing it into our memory arrays. So you can picture a giant matrix where you have inputs and potential outputs. And when things are correlated, you can identify those as hotspots in our memory array. And so that's probably closer to saying if you could measure signals coming out of the brain and then be able to correlate those with other activities, you could make a snapshot of what's going on. And if you can do that in real time, it'd be even more interesting. And maybe that would even give you the opportunity to reverse engineer something later if you had a problem. And so that, I think it's probably one of the ways that we're closer to what you're talking about.
Good.
That's intriguing. I think Sorrel Chesson has a question. Sorrel, would you like?
There he is.
Yeah,
there you go,
Sorrel.
Sorrel, you should be good to go. Sorrel, are you with us?
Well, perhaps he can't
He might be having.
Can't voice his
unmuted.
question, but his question was, how do you and your colleagues feel about returning to the university?
So I'll attempt to be as diplomatic as possible.
Yeah, don't forget we're recording this, Nate, so.
I'll start with the fact that I started here in 2006, and so we were a part of UAlbany when I started. I got my tenure in 2012 as a UAlbany professor, and so we have a lot of us have a lot of roots as being originally UAlbany professors when we first started out here. So that's what I'm speaking of the faculty. In many senses, the proximity to UAlbany is very attractive versus the proximity to our sister campus currently. So currently we're 90 miles from Utica, which is where students do a lot of their gen ed coursework, and where many of our colleagues are now located, who are part of the university there in Utica. And so there is definitely an attractive component of being able to be part of UAlbany again, and have that close proximity to campus and resources and faculty colleagues over there, as well for our students to be able to cross back and forth. I think we've done a pretty good job making things work under the current way that SUNY Poly is organized, and I would say that we've actually found a lot of connections with faculty colleagues there as well, and some opportunities for our students, especially through a lot of the distance learning. So there have definitely been positive aspects of being part of SUNY Poly in Utica, but I think there's also a lot of attractive reasons why going back to UAlbany would be something good for especially our students, but also from a faculty and a collaborative type of experience. It is nice to have your colleagues directly across the street and easy to connect with. So I'll leave it at that. I think there's pluses and minuses both ways, but there's definitely some advantages to potentially becoming part of UAlbany again.
Great. Any other questions? I don't see any. Do you see any, Sorrel?
No, I don't.
Okay, well, Nate, actually, I did another one. You touched on this, how because of the pandemic, there's a great shortage of chips that are sorely needed, and like smartphones and cars.
Yep.
And that one of your partners, Applied Materials, I think, is planning to help address that. But it sounds like what they're doing at your facility and what most of your colleagues are doing is really more the R&D side as opposed to the commercial manufacturing side. Is that correct?
There's kind of two aspects. So I would say in general, yes. So most of the people here doing work from our partner companies are doing R&D, but R&D doesn't always mean they're coming up with a completely new piece of equipment or a completely new technology. Sometimes that R&D is for throughput. So maybe they're making a process better or faster. So when they go to manufacturing scale, they're able to produce more chips, or they're able to, yield is the term they use here. So this is kind of like saying that 100% of the cars that roll off your assembly line actually drive properly. With making chips on one of those wafers I showed you, you may make thousands of chips on that wafer. And so if you're getting a yield in the 90% to 95% range of those chips working, you're doing pretty well. So any advances here that can make yield better or make the throughput faster would go directly to address the chip shortage. But in the most direct way, the way that companies like Applied Materials will be part of this addressing the shortages, they'll be selling a lot of equipment to companies like Intel, who are going to build new fabrication facilities. Global Foundries is set to expand up here in Malta, New York, so they'll be selling tools to them. So they're really in it from a sales perspective. It's the companies like Global Foundries and Intel. Some of you may have heard internationally of Tokyo Semiconductor Corporation, or TSMC. Those are all the either foundries, we call them, or chip fab facilities that are the ones that really have to invest in new or bigger plants to be making more and more chips. And at a federal level, so I've been involved in this from a SUNY-wide effort. The U.S. government is planning to make investments in the semiconductor area. There's Senator Schumer put in a bill called USICA. It's the United States Innovation and Competition Act. And that's set to fund, as long as it gets appropriated, funds to support not only the industry, but also the R&D leading to advances in semiconductors. So SUNY is really trying to make a play for being part of that. And some of you may have seen in the news that Senator Schumer came last week with representatives from Department of Commerce to tour the facility. And so I think we're definitely primed to be a player in whatever initiatives come down, because we already have the site that's made to do this type of R&D. And so hopefully that comes to fruition, and hopefully it really does address the need of being able to address the chip shortage and other aspects of it.
Yeah, because you're right. I think I've heard too in the news that the manufacture of chips has actually become a national security issue. And I think both the administration and Congress want a much greater domestic production of chips so that we're not relying on Taiwan or other countries for that.
Correct. Yeah. And then that's the biggest issue right now is, we went from being a reasonable player internationally, so as a country, as a chip producer, to being now in the tens of % range for a total number of chips manufactured worldwide. So, not only for an economic perspective, but also for a kind of a security perspective of being able to build our own chips.
Yeah, and I think I've read too that China wants to build its own capacity, so I could see a rivalry there. Okay, I think
chip race.
Chip race,
exactly. I know knowledge.
Exactly.
Yeah.
Dean, I think John Bartow has a question. Do you see that too under chat?
Yes, I do. I seem not to be able to unmute him. Can you?
Okay, I'll go ahead and do it then. Okay, John, I think you can unmute now and ask Nate your question.
Well, gee, I would have thought, hi, Nate. I would have thought it'd be better for you guys to read it. Nice to see you again, man.
Good to virtually see you.
My question's this. My instincts would tell me that the potential impact of the organizational change on doctoral education and doctoral students working with you or other members of the faculty would be absolutely minimal, that the life of the doctoral student is tied up so much in the research with the faculty group that they'd be oblivious to any change. Is that correct?
Yeah, I assume so. I mean, I certainly haven't seen any of the details of planning of how this might come to fruition. But if we do merge back with UAlbany, I assume it'll be similar to what we did when we left UAlbany and joined with SUNY IT, is that we did a teach out as faculty for the remaining number of years to basically teach out all the undergrads who started at UAlbany and were still had the option to complete the degree with UAlbany. I assume we'll do the same thing if this goes forward for both our undergrads and grad students. And you're right, especially the graduate students, they see this less as they're less coursework dependent and more dependent on doing their research activities in the lab. And so usually it doesn't come up until graduation. You have to figure out which system we're looking into. So are we in DegreeWorks or are we in whatever the other program, to figure out if they've satisfied all the requirements. And we used to call you or somebody else over at UAlbany to make sure we had filed all the exceptions. So yeah,
you just get a different printer for the diplomas, and you're good, I think. But before I'll mute myself or let Ed mute me. But your presentation was wonderfully interesting and good to hear you speaking again, man. But the nature of what you're talking about is just so overwhelmingly invigorating. It's nice to hear. Thank you.
Thanks, John. It's nice to see you.
Okay, great. And Dean, I think David Wagner has a question. Let's see. Okay, Dave, I think you should be able to talk. Yep.
Yes, I assume you can hear me now.
Yes.
Yep.
Okay, this is a very different kind of question. I'm glad I retired when I did in the fall of 2019 because I avoided all of the hassles that Albany has had to go through with regard to dealing with the pandemic, to what extent and in what ways has Nano had to deal with the same issues?
It's a great question. It's we were lucky in a sense we do so much graduate-based education. I told you the numbers were pretty small for our undergraduate program. Our graduate program we're currently at about 150 students, I think. Since we have that large research focus, and because the entire site over here was designated as a research site, we had an exemption to be able to continue to do work in person fairly soon after all of the shutdowns. So I think it was probably April in 2020, right? So April 2020, I was back in the lab doing a lot of work, and my students slowly came back. Everybody's had the option to work remotely if they wanted to, and I think the undergrads probably bore the most impact because they were the ones who had the most course-intensive schedule, and so had more of the, I wouldn't say issues, but more of the issues with having to do remote coursework. So teaching wise, we were able to set up classrooms and everything to do distance learning in a better way. So that I think we had that covered pretty well. But we really lucked out from a research perspective. If we wanted to be back in the lab, we really just had to follow COVID protocols of number of people in the laboratory and daily screening and testing. We did biweekly testing for quite a while and still are doing it now. So it's had minimal impact on research, which is good.
I would expect that some aspects of it would be easier for the Nano people to deal with, because you're accustomed to having to deal with clean rooms and being prepared to protect yourself against just about any kind of interference with what you're doing. I had a colleague in my own department who got so flummoxed by the things that they had to do. He was getting near retirement, was going to wait another year or so, but he decided he was going to retire at the end of the fall semester because he just couldn't take this anymore. But I don't think you had to deal with it quite that way in Nano.
No, I think we had one faculty member this year who decided to call it quits, and I think in part because of the it was more of the remote teaching aspects. But yeah, for the most part, people were used to, we're a secure site too, so everything is badge access, you go through security and stuff. So there's a little more of that feeling already of going through restricted spaces and dealing with that. So I think you're right. It was a little easier for folks over here just to be used to it.
Well, I'm glad you're able to keep doing your work.
Thank you.
Okay, I don't see any other questions. Do you?
No, I don't either.
Okay. Well, it's after 2:30, so I think we'll let Nate go. Again, thanks very much, Nate, for a great talk. And
no problem.
I for one look forward to a reunification of Nano and UAlbany. And I suspect that much of the Emeriti, share that feeling. Dean, anything you want to add to
No,
Nate?
I again, my thanks, Nate. Sorry, we had some technical difficulties along the way, but everything worked out. And as I said, I learned a great deal. Speaking as a social scientist, not a physical scientist or a biologist, I learned a great deal, and it really boggles my mind of where we are. When I started at the University of Albany, everything was paper, and that was 1968. And wow, look at where we are now. So I really appreciate your talk and everything I learned from that, and I'm sure the Emeriti appreciate it as well. Thank you.
You're welcome, and I would invite, when we're not under COVID rules anymore, if you guys would like to come over for a visit and tour, I'd welcome you back. So
Absolutely.
That sounds good, actually.
Yes.
Yeah, great.
Yes, indeed.
Okay, and I guess before we end the webinar, just coming attractions. Our next webinar is in 2 weeks, right? February 14th.
Yes.
And we actually have a very special speaker, Dr. Joachim Frank. He's actually a Nobel Prize winner in chemistry. In fact, to my knowledge, that'd be the very first time the Emeritus Center has had a Nobel Prize winner speak to the Emeriti.
Yes.
he has an Albany background, and in that he did much of his work at the Wadsworth Center and Department of Health, and also was a faculty member in our biomedical sciences department in the School of Public Health. I mean, he's currently at Columbia, but still very active and still has a connection to Albany, which is why he wants to come join us. But he's what I would call a true Renaissance man. Not only is he a Nobel Prize winning chemist, but he's also a published novelist, a poet, and a photographer. And when he accepted our invitation, he said, everybody wants me to talk about my science. What would it be okay if I talked about my more creative activities? So he is going to be talking to us, I think, about some of the books that he's written, some of his poetry, and some of his photography as well. But I'm sure if anybody has a question about his Nobel Prize winning work, he'll entertain that too. Anything else to add for next week? I mean, next 2 weeks presentation, Dean?
No, I'm looking forward to that too. I mean, his title is interesting, The House That Jack Built. And when he sent us his title, he sent a picture. So
Yeah,
my guess is he's going to have some photos as well. So it should be fun.
be interesting what a chemist has to say about the writing novels and poetry and photography. In any case, all right. Well, thanks everybody for attending. Stay warm.
Thanks, Nate.
We'll see you in 2 weeks. Thanks, Nate. Bye-bye, everybody.
Take care.
Take care. Bye.